Okay, so this is unit 2.3, number 9. It's another subgroup proof. Let's see if I still have this here. Nope, I just inserted it in itself. Let me grab this real quick. So copy that, paste it here. There's our definition of subgroup. Okay, so actually, I'll move that a little bit up. Okay. So in this one, we have, you take any element x and g, and then you multiply it, any element where you can take xa times ax, where a is already fixed, then that x belongs in this subset. And we're trying to prove that this subset is a subgroup. So let's take a look at how we do this. So first, H has to be closed. Okay, so in order to show H is closed, let me write this, is H closed? Okay, well, to check that, we're going to pick two elements in H. So since A is already taken, I'm going to pick my two elements, let B and C be in H. And we want to show that B times C, BC, is also in H. Notice I'm doing that lazy mathematician thing where I'm leaving out the stars. It's all implied there. Okay, so how do we show that BC is in H? Well, we need, if you think about what it means to be in H, then it means that for some fixed element of G, A, right, that if BC is going to be in H, then I want to show that BC times A has to equal A times BC. That would guarantee that BC is in H. Okay, so this is my goal. This is my goal, right, for closure. And I started with B and C are in H. So if B and C are in H, ooh, that tells me that using the rule right here, that tells me that B times A equals A times B, and C times A equals A times C. And remember, A is not any random element, it's a specific element. You don't get to pick it. It's set in stone there. So that's what we have. That's by definition of what H is. Okay, so somehow I have to be able to take these guys and manipulate them to get this. Okay, so let's think. How can I do this? Well, I'm going to try to isolate one of these A's here. So why don't we try, I don't know, this one. So in order to isolate that A, let's do CA equals AC. And then on both sides, I'm going to multiply by C inverse. So now I've got A times E, which is really A, equals CAC inverse. Okay, so now I have a form for A. So let me plug that in somewhere else. So let's see, where could I plug that in? Let's plug it into this A over here. So this combined with this is going to yield the following. BC CAC inverse equals AB, like that. Okay, so all I've done is I've plugged in that into there. Do you guys see that, hopefully? So, okay, so now I can manipulate this some more. I don't have any C inverse in the goal that I'm trying to get. So let me get rid of it again. BCAC inverse, let me multiply that by C on the right. So that's going to be AB times C on the right. And then this is going to turn into E, which multiplied by anything is the anything. So that's BCA equals ABC. And that's what our goal was. So this proves that BC has to be an H also. And so therefore, H is closed. That's usually the hardest part of the subgroup proofs, is proving that it's closed. So that part's done. Let's take a look at if the identity of G is an H. Okay, so let's see. How do we do this? Well, in order to be an H, you need to pick, your elements have to have the property x times a equals a times x. So we're checking if E is in there. So it's in there if E times A equals A times E, which is true. So just based on the definition of what H is, E is in H. So we're good. Then the third one is if A is in H, then is A inverse in H. So we're going to let A be in H. Oh, sorry, probably shouldn't choose A. Let's choose B. So we're going to let B be in H. Want to show B inverse has to be in H. Okay, well, the only way B inverse is in H is if B inverse A equals A B inverse. That's the only way we're going to get that. That's our goal now. Okay, so let's take a look. If B is in H, then I know that by definition of being in H, BA equals AB. BA equals AB. All right. So, I don't know, let's throw an inverse in front of everything. So B inverse BA equals B inverse AB. And so then this part's going to turn into E times A, which is just A, equals B inverse AB. And then let's throw a B inverse on the left side of everything. So AB inverse equals B inverse AB B inverse. And then that's going to turn into E. So now I'm just left with AB inverse equals B inverse A. Well, if you think about it, that's what I'm trying to prove. B inverse A equals A B inverse. That's what this says, just, you know, with the sides switched. So that's enough to prove that B inverse has to be in H also. So if B is in H, B inverse is in H. Well, that's part 3. So then you just need one more statement. By 1, 2, and 3, H must be a subgroup of G. G's the original, right? Yes, H is a subgroup of G. Okay, hope that helps.